What we're going to have a quick look at today is just some ideas, more curve sketching ideas, but this time polynomials, specifically what to look for with a polynomial. So y equals some polynomial x. The first obvious one is the y-intercept. Will always turn out to be the constant number, because obviously if you substitute 0 into every other term, you're going to get 0. So that's, I guess, the easiest piece of information about a polynomial. So let's use this one as an example. Now I don't actually need to expand the whole thing out, of course, to find the y-intercept, because I know when I do expand the whole thing out, if I was to do it, I'd just be going constant times constant times constant. So we can look at this and go 1 times minus 1 cubed times 2 squared, which is, of course, and that should be our y-intercept. There we go, down at minus 4. So that's the easiest one. Now, the x-intercepts, of course, are the solution to solving the polynomial equals 0. Now, fortunately, our one was already factorised, so that makes it nice and easy. So we've got negative 1, so that's the x plus 1 equals 0. Positive 1, that's the x minus 1 cubed equals 0. And negative 2 would be the solution for the x plus 2 squared. Now, if I have a polynomial that I can't factorise, and I suppose that's certainly possible, an estimate might have to do roughly a cut here and so on. As x approaches plus or minus infinity, so as we're out of the extremities of the graph, the polynomial will always act like the leading term. That has something to do with an idea called dominance. So when you want to find out what a graph does, you're looking for which term dominates, and the term that dominates is usually the one that is the steepest. And so when you talk about a polynomial, the one with the highest power would be the steepest. So it'll act like the leading term. Now our one, again, I don't need to expand the whole thing out. X times x cubed times x squared gives me x to the power of 6. So if I was to say to you, hey, draw y equals x to the power of 6, we know we would start up here and we would finish over here. So we know our graph will do exactly the same. So it'll do exactly like the leading term does. Okay, now the roots themselves, the actual power on the roots tells me how it meets the x-axis, the type of root it is. So if it's an even powered root, then it will come down and touch it. So if it was a double root, it would be like a parabola. If it was a quartic root, so say it was to the power of 4, it would be a U shape, a little bit flatter at the base, steeper at the sides, and so on. So it'll act like the power. So on ours, x plus 2 squared, so over at negative 2, I know it's going to come down and touch like a parabola. I also know it starts up at the left-hand side there, so I know, all right, it must do something like that at negative 2. Similarly, odd powers, other than the power of 1, of course, will do that inflecting sort of shape. Power of 1, well, it's a linear function, it just cuts like normal. So it will inflect at the odd ones. We've got x minus 1 cubed. So at 1, now we know it finishes up the top here, so it must come through like that. And then I say over at negative 1, it's just a straight line. So we can put all that together, and there's our final graph. Now, where exactly this turning point down the bottom is, and the one up the top here, once we look at calculus, we can identify those exactly. But for a rough sketch, I guess we're just guessing whereabouts they would be. Okay. Now, if of course we can factorise it as a perfect polynomial, so x minus a to the power of something, well then we know it'll just look like the basic curve, but we've got a shift left or right happening. So if it happens to do that. So we talked a bit about inequations yesterday. It now opens up an idea like this. It's an unusual inequation. X minus 1 squared, x plus 3. But we could use a graphical way of doing that as well. Just like we did with the quadratic one. Where we say, oh, let's think of it as a parabola. When is it above? When is it below? We could do the same with this. So if I was to draw this graph, I know it's got an x-intercept there at 1. It'll be a double root. Over there at -3 it'll be a single root. I'm not really, just like with the quadratic ones, I'm not really worried about the y-intercept. It's more the shape of the graph now. So where does it start? We've got x squared times x, so it'll go like a cubic. So it'll start down at the bottom, finish up at the top there. And so what we're saying is, hey, when is this graph below the x-axis? So it's equal to as well, so we know 1 and -3 is included. When is it below? Well, actually it's only below for a tiny little bit there, less than -3. But don't forget about the single solution there of x equals 1. That is a solution as well. So our final solution, less than or equal to -3, or x equals 1. It gives us another way of approaching in equations. And that'll do us for today.